Okay. Magnetic force and centripetal force. Let me give you a recap of what we were doing in the class yesterday. Mm, okay. Okay, I remember when I was student, I always wished that there should something be that class is cancelled or something. But uh,
Yes, exactly.
okay, so that's we don't want to cancel it ourselves. We want good things to happen to us rather than we doing the good things to ourselves. Listen, this is a recap of what we were studying in yesterday's class. There is a north pole of a magnet on the top, there's a south pole at the bottom, there's a uniform magnetic field between them, and a charge particle, an independent charge particle. Before this, we were studying that charge particle is going within a conductor. But now there's a free charge particle, like it can go wherever it wants to go. If there's a force on it, it can change direction of motion. It cannot be in the case of a conductor. In the conductor, charge particle is supposed to stay in the conductor. Now, what will happen? And we discussed that yesterday that if the charge particle will enter a magnetic field, it will experience a force. Provided that charge particle is moving perpendicular to the magnetic field, it will experience a force which will be perpendicular to the magnetic field as well as the velocity of the object. The force will simultaneously be perpendicular to both of them. So the magnetic field in this case is towards the screen, into the screen. Your fingers should be tapping into the screen, and your palm should be pointing towards right, and you see that initially the force is upward. And I'm using that left hand Fleming rule, left hand Fleming's palm rule. Okay. Now your palm is pointing towards right, your finger is tapping into the screen right now. So your thumb is telling you that the force will be upward. But what happens after some time? Because this charge particle is not moving in a conductor, it is free. So what happens is instead of moving in the original direction, it starts moving in a new direction. But according to new direction, the new force is also perpendicular. It's not that the force is always in the same direction. The force is changing direction and it is always being perpendicular to the velocity. And we have discussed that. If you remember, the first topic of A2 was that what happens if there is a force perpendicular to the velocity. And we know if there is a force perpendicular to the velocity, it will never be able to increase the velocity or decrease the velocity. Such force can only change direction of motion of an object. So what happens is, instead of moving in the original path, object deviates from the original path and starts moving in a curved path. And when we observe that curved path, we find that it is an exact part of a circle. It can be a complete circle. Some charge particles, they can go like this. So this means they are having a very large circle. Some charge particles can go like this. So it means they are having a smaller circle. Some can do this. So these charge particles are either slowing down or they were not perpendicular to the magnetic field. So they are moving in a spiral. Okay. They are drilling themselves along the direction of the magnetic field. They're going down as well because they were not, or they can be moving up as well. Like they're either coming towards you, spiraling up or spiraling down. So all these things can happen. Okay. We will be discussing how, listen, even this, you might say that it is a curve path. No, it is not an ordinary curve. It is an arc of a very large circle. Okay. Now, the force on a charge particle when it goes into a magnetic field depends on the size of the charge on the charge particle, its velocity, its magnetic field density, the magnetic field density that it is moving in, and angle between the velocity and the magnetic field as well. Okay. So when we connect them all, we get force on a single charge particle is BQV sine theta. Okay. Now, when charge particle goes into a magnetic field and moving perpendicular to the magnetic field, it moves in a perfect circular path. I have used word perfect circular path. Why perfect circular path? Perfect circular path means that it is moving perpendicular to it's moving perpendicular to the magnetic field, and there is a force which is perpendicular to the velocity. So when there is a force perpendicular to the velocity, it is also the centripetal force. And it is very rare these days that examiner ask a centripetal force question. I think there was one question in 2020 or 2021 about centripetal force. Normally, these questions are now getting extinct. Examiner does not ask a centripetal force question. You know why? Because centripetal force question can touch gravitational topic. They can touch the electrostatic topic. They can touch oscillation. They can appear in magnetic field. So this is why that is the first chapter. Number one. Number two, we don't have very recent questions of circular motion. The reason is that examiner does not give circular motion question. He mixes it with the gravitation or magnetic force question. Now, there is one more mix that we will be doing today. Magnetic force is equal to centripetal force. And we are taking a case of where the charge particle is perpendicular to the magnetic field. If a particle moves perpendicular to magnetic field. The reason I'm using perpendicular is that I want to get rid of that sine theta part, okay? For the simplicity, it will be B QV equals to MV square over R. Okay. So I need two expressions, and you have to find them and then share with me. I need an expression for R, and I need an expression of Q over M. Find these two expressions and share your working. You can share the picture of your working with me in the group. So these are the equations that you can find. Now, when I was student, I don't know about you, but when I was student, I always thought that how do we measure or how do we know that electrons can move up to 1/9 of speed of light? And if they can, how can we find their speed? How do we know that a charged particle, alpha particle emitted from a nucleus has so and so speed? Like, do we do that distance divided by time thing over here? Answer is no, we don't. That we cannot measure, like we can now, but that is not how we do that. Like there are easier way of measuring speed of a charged particle. What we do is uh, another more accurate way is coming your way, but this can also be used if we know the strength of the magnetic field. If we can find out the radius of the curved path charged particle is moving at, and if we know the mass of the charged particle, we can use that data to find speed of the charged particle in the magnetic field. Now, what do we learn from here is, as as m over bq is constant, pay attention. Mass of the charged particle, same. It is moving in a uniform magnetic field, same. Charge of the charged particle is also same. So m over bq, whatever this number is, for that particular charged particle in that magnetic field should always stay the same. So if m over bq is constant, r is directly proportional to v. Pay attention. R is directly proportional to V. So if we have this is how on the basis of this we can make a speed selector. Speed selector. If we have a uniform magnetic field like this, and assorted charged particles are coming in from here. Assorted charged particles. All with same mass. Actually, I should change this thing. Moving charged particles, all with same mass and charge, but sorted speeds. So they have different speeds, but they all have same charge and they all have same mass. So what happens is when charged particles, there is a magnetic field here. This is a magnetic field. It doesn't matter whether it is in or out right now.
Sir, could you go back? Could you go a little left for a second?
Is that okay?
Yeah, okay, thank you.
Now, this will be if this is the first line and there is the last line, and all other charged particles are in between. Then remember, this one will be the slowest, and this one will be the fastest. Because which one has the bigger radius of curvature? Which one has a bigger radius of the curvature? Which one will be moving in a bigger circle? So if this is X and this is Y, then Y should be moving in a bigger circle. So Y has a bigger radius than X. Now, if we have a gate over here, Okay, and we can move the gate here and there. This gate can move forward and backward. So this is a single gate with one opening. So what will happen is specific charge particles with one particular specific speed will manage to come out. And remember, when they will come out, they have no other reason to change their direction anymore. They will start moving in a straight line. As soon the charged particles they come out of the magnetic field, select it, speed, gate 2, gate 1. Gate 2 is stopping, too fast. Particles. Gate 1 is stopping, too slow. Particles. Charged particles are they go into the magnetic field, they move, and they change their direction. Listen, when they all were moving in the same line, there was no reason we could differentiate between the fast one and the slow one. They were moving in the same beam. But now, when they go into the magnetic field and they deviate from the original path and they move in the different radii, with any particular speed, okay? So this is known as speed selection or speed selector charge particles in magnetic field. So let's do something new now. I will be bringing cross fields now. What are cross fields? Let me save time by copying this diagram from here. Okay. Now we have another plate here. So we will be attaching further plates on the side, an electric field to compensate the effect of magnetic field. Okay. So we have this plate here. We have this plate here. Hmm. Okay, let's follow again. And this is the okay. I hope you can see what I'm trying to make here. This is the same south side of a magnet, but now there are two plates between north and the south magnet. Does it look like that? That like there are north and south are horizontal, and the plates on the sides are vertical. So I can connect these plates to a DC power supply. Okay. So two plates are connected to DC power supply. So this is what is happening. This is for you for understanding the structure, but there's no way I can explain what is happening in 3D. So I will be making some 2D diagrams now. This is where the particle is going in. Okay. Now, this is just a 3D explanation of what is going on over here, but I have to make a two-dimensional diagram to explain. So this rectangle is showing the magnetic field. This rectangle is representing one plate. This is the other plate. Okay. Now, if there is a charge particle coming in, for the simplicity, it could be any charge particle, but I'm for the simplicity making it positive. A positive charge particle is coming in. There is a magnetic field. A cross magnetic field means it is into the plane of the paper right now. So if there is a magnetic field into the plane of the paper, and there is a charge particle which is moving to the right, what should be the direction of magnetic force on this charge particle? So if your fingers are stabbing into the screen and your palm is towards right as the direction of the velocity is, the force that it should experience should be upward. So force is upward. And remember, this is magnetic force. I will name it Fm. Okay. And don't forget it is a positive charge. Now I have to induce an electric field using the top and the bottom plate, which will counter the force that is acting on this charged particle. So, can you help? Which plate should be positive and which plate should be negative, so that so these two can cancel the effect of magnetic force over here?
The bottom one should be negative.
The upper one should be positive and negative.
Why? Can you explain why?
Mm,
Do you think when upper one will be negative, what will be the direction of force on the positive charge because of the electric field, upward or downward?
downward.
So positive and negative, they hate one another.
No.
Or they love one another. Remember, charges are perfectly straight. They don't like a positive charge, does not like another positive charge. They always like negative charge. So positive charge should be repelled downward. So there should be a positive plate on the top and negative plate at the bottom. So there should be a positive plate on the top and a negative plate at the bottom. So what will happen? This will produce an overall downward electric field, and electric field always exert a force on positive charge along its own direction. So that will produce an electric force downward. So here we have a screen. This is a screen. Some of the charged particles end up here. X. Some end up over here. And some end up over here. This is Y. This is Z. Now, what is the story for the particles, particle X? What is the story for particle X?
It's negatively charged, maybe.
No, no. It has more magnetic force than electric force.
Oh yes, yes. So the
Okay.
magnetic force is BQV, right?
Yes.
So maybe it's
So,
charge was greater or velocity was greater.
yes, because magnetic force is not only affected by the charge, it can also be affected by the velocity. So it might be it can be a reason of velocity. And if all the charged particles are identical, for example, they are all alpha particles, we can say that X particles are faster than rest of the particles. So for particle X, magnetic force is more than electric force, now what about particle Y? For particle Y, magnetic force is less than electric force. Magnetic force is less than electric force. Now, what about particle Z?
Magnetic force is equals to electric force.
Magnetic force is equal to electric force. Now, remember, magnetic force is BQV. Electric force is EQ. And E is potential difference divided by distance. We will be bringing that thing later into the situation, but right now, for particles ending up at the BQV equals to EQ. What do you think has become irrelevant over here?
Charge.
The charge is totally irrelevant. Whether charge is more or charge is less, charge is positive or negative, doesn't matter. It is totally irrelevant. The only thing that is making all these differences is speed of the charged particle, which is E over B. So this is the solution for the speed of the charged particles. If you are looking for speed of the charged particle, all you have to do is just measure the strength of the electric field, measure the strength of the magnetic field. To measure the strength of electric field, all you need is use.
Assalamu alaikum, sir.
Wa alaikum assalam.
Sir, I've been trying for the last past half an hour to enter, but Zoom keeps telling me error, error, error. I even sent you a screenshot.
Listen,
No, sir.
I have to repeat. I have to repeat because this part might not be recorded. So we have reduced the formula to speed equals to electric field strength or electric field divided by magnetic flux density. Electric field strength divided by magnetic flux density, and when I was thinking that how I'm talking about when I was a student, and I thought that how do we measure speed of an electron, which is moving at 1/10 of speed of light? Like it can go around Earth in less than a second. Then how would somebody can measure speed of that kind of speed with distance and time? So this is the answer to my question, that we don't use distance and time. What we can use is electric field density and magnetic flux density. How do we find electric field density or electric field strength? We need because this electric field is produced by the two parallel plates. We need the potential difference between the plates. For that, we can use a voltmeter, and we need distance between the plates. For that, we can use a ruler. So when we find voltage and distance, we can divide these two, and we can find electric field strength. Now, how do we find magnetic flux density? For that, we use a Hall probe and a CRO, or sometimes we can also use Hall probe with a voltmeter, but CRO is better. This is how we can find speed of the charged particle, which is moving very, very fast. And these things are very easy to measure. Like, you don't need to be very, yes, you need to be very skillful to set this apparatus, but to measure these quantities, it is very easy. So this is the solution for finding speed of the charged particles when they are moving in cross field. Why do we call it cross field? Because the electric field and the magnetic field, they are perpendicular to one another. Look, magnetic field is from top to bottom, and electric field is side to side. So this is why we call it cross field. Okay. So now that's it for today, because in the next lesson tomorrow we will be doing Hall voltage and Hall effect.
Okay, sir. So are we done for today?
Yep.
Okay, sir. Assalamu alaikum. Have a nice day.
Walaikum assalam. Thank you.